Property rights, fair transactions, rule of law, the underpinnings of civilized existence have for thousands of years depended on the ability to keep and reference accurate records. Scribes documented tax payments, property ownership, and marriage agreements. These records created trust in contracts. Trust allowed for cooperation, and cooperation enabled progress. But for records to be useful, they must be trustworthy, and this requires a central source of truth, an authority to keep the official account and settle any disputes. Bank balances, passports, and house titles, for example, are all records that require a reliable central authority. Without a central authority, records can be forged or manipulated. In a famous early 20th century example, con artist George C. Parker successfully used forged documents to sell the Brooklyn Bridge multiple times. Without a clear central authority to authenticate ownership, documents are worthless. They really don't prove anything. Record keeping might not seem like the most thrilling topic, and you might be wondering what this has to do with blockchain, one of the most emergent and dynamic topics in technology today. Well, behind all the buzz around blockchain and Bitcoin is a simple fact. Blockchain is just a new form of digital record keeping. Digital records themselves are not new. Modern databases allow us to efficiently store, share, and search through massive amounts of information. However, all these digital records rely on a central authority to keep the data safe and be the source of truth. Blockchain, a different protocol for digital record keeping, offers something new. It creates trust in records without a central authority. In 2009, a researcher noticed that this combination, high trust without a central authority, had a unique potential. Blockchain could be used to create an alternative system of currency, one that operates without any governing body. The researcher, known only by the pseudonym Satoshi Nakamoto, called his scheme Bitcoin, and a blockchain movement was born. While Bitcoin is the most commonly recognized application of blockchain technology, it is merely the tip of the blockchain iceberg. In this module, we will explore this iceberg by answering 3 questions. What is a blockchain? How does it work? And how can it be applied to global industries like finance, supply chain, healthcare, and government? Blockchain is a record-keeping protocol that, like traditional digital records, can be used to represent data of nearly any type. There are already many blockchains in use today, recording information ranging from financial transaction data to legal documentation. A blockchain is like the next-generation database, with a few distinguishing characteristics that allow it to create agreement around and trust in a data source without a single central authority. While blockchains are not effective for housing massive amounts of data, say a large video file, they are effective at storing critical information in a highly trusted, secure way. A blockchain might be used to create a record of who created a video, but not the video itself. To understand how blockchain protocol can create trust without a central authority, let's take a simplified example. Imagine that 100 people are establishing a new town on undeveloped land. They've divided up the plots and need to document who owns what. One option is to create a central database and then make 100 copies, one for each townsperson. But since the copies would be easy to alter, the single original version would need to be kept safe from tampering, requiring some sort of central authority. But imagine if someone in the town claims that there is a way to establish a trusted source of truth without appointing any central authority. In fact, she says we can come up with a way, a protocol, that'll make all 100 copies equally reliable where any data disputes would be resolved among the group. What would it take for something like this to work? For one, each copy would need a built-in way to signal when the data changes. That way, instead of constantly cross-referencing all the data in all of the copies, the townspeople can simply look for the signals. No signal, no changes. 2. They need a way of making group decisions about proposed changes. If and when signals go off, how will they determine whether to reject or accept the change? For example, in the case of a legitimate sale of the plot to a new owner. Blockchain protocol establishes exactly this type of digital record. And these 2 attributes are what make it possible to create trust without a central authority. The word blockchain is used to describe both the protocol for record keeping, meaning the way of storing records, and the record itself. Each individual blockchain operates under a version of blockchain protocol. Let's look at how, in practice, these blockchains create trust without any central authority. Blockchains are ledgers that store data in blocks, stacked end-to-end. Blocks are never edited or deleted. Updates to the data, for example when plot ownership changes, are not recorded by editing the previous blocks, but instead by adding new blocks carrying information about the changes. The blocks are linked together, hence the word chain. Each block is designed so that any changes in the data will break the entire chain, raising alarm bells. Here's how this works. Consider any two blocks on this particular chain, block n and block n plus 1. Each block is recording changes in plot ownership and consists of three distinct parts. 1. The data about the change. In the case of block N, that plot A was sold to Morgan and plot B was sold to J. 2. The second piece of information is a conversion of that data into a unique identifier called the hash. This is like the block's fingerprint. A cryptographic method such as SHA-256 generates the unique hash based on the underlying data in the block. If the data changes, the hash changes. The last piece of information is the hash of the previous block in the chain. Each new block added follows this pattern and is linked to the previous block. This is the link that will be broken if the data is changed. For example, imagine attempting to change the buyer of plot A to Mike. The change in data would automatically change the hash, and suddenly the link to the next block in the chain has been broken. A broken chain is a clear signal that the data has been altered. To tamper with one block, you'd need to first restore the links in the chain by tampering with all the subsequent blocks, and then convince the majority of the townspeople to accept your new proposed chain as the source of truth, a nearly impossible feat. Since it is nearly impossible to change blockchain data without common agreement across the network, blockchains are described as immutable. In other words, unchangeable. Since in most cases the people with a copy of the data, called the nodes, are not related or otherwise organized, blockchains are described as distributed. The immutability and distributed nature of the blockchain mean that trustworthy data can be kept without any central authority. This type of decentralization has the potential to remove middlemen or central authorities that exist, like payments without using banks, or to create new ways of organizing previously disconnected groups, like linking farmers with other actors in the supply chain. We've established that blockchains are decentralized record-keeping containers. In a traditional database, a single administrator is in charge of approving and processing changes to the underlying records. In a blockchain, the network as a group replaces this single gatekeeper. Let's take a look at how records are stored and added to the blockchain. Records are stored in a distributed way. Each holder of a registered copy of a blockchain is called a node. Nodes have full access to the data in the blockchain and maintain their own copy on their own devices. Say that the members of the town are all nodes, including Morgan, Jay, Mike, and Deb. Any one of them can propose adding data to the blockchain in the form of a new block. Say Morgan buys a plot from Mike. To record this change in ownership, she adds a block to her version of the blockchain. So then what happens? Well, nothing, unless the majority of the nodes agree to this block and the underlying data. If they don't agree, they will simply not replicate Morgan's changes on their own versions, thereby rejecting the proposed block. When the network as a group approves a new block, individual nodes will update their own copies, effectively syncing with the latest source of truth. To better understand how this works in practice, imagine you want to pay a friend 1 Bitcoin, the cryptocurrency encoded by the Bitcoin blockchain. This payment eventually will be recorded in a new block on the chain, batched together with 1 to 2,000 other transactions. Before the network can decide to add or reject the block, they need to be sure it is valid, meaning the data is true and consistent with the rest of the chain. In this case, do you have enough Bitcoin to actually make this payment? Are you who you say you are? Information about your attempted payment is instantly shared across the network, and your transaction joins a pool of other unconfirmed transactions. Nodes in the network will work through this pool, validating your and other transactions by working through the cross-checks established by the blockchain protocol. For example, on the Bitcoin blockchain, one piece of the validation step is ensuring that the transaction is approved by both you and your friend. This is done via a digital signature process that requires a valid private key which is unique to every person and invisible to others. The network can confirm if a transaction is approved with a specific private key without seeing the key. This signature ensures that only you can transact with your Bitcoin. Any of the nodes can chip in to help review and validate transactions. Sometimes, however, more hands make more problems. Consider that as the network grows, more transactions are being added and more nodes are involved in validation. Imagine being in an increasingly crowded auction hall where everyone is independently trying to buy and sell the same goods. Some control is required. For example, how can the network avoid simultaneously processing conflicting transactions or transactions that are double spending the same Bitcoin? Blockchains like Bitcoin must establish a protocol called a consensus mechanism for clarifying roles in validation. This is like assigning an auctioneer. This is effectively a way to force the network's attention to one block at a time. Bitcoin uses a consensus mechanism called proof of work, which focuses the network's attention by selecting a single node to propose each new block. The selection is done via a puzzle. Whoever solves the puzzle gets to add the next block. Sounds fun, right? The puzzle, a built-in cryptographic algorithm, converts input numbers into unique output numbers. The only way to find the winning output number is to input random guesses. This is like a really difficult dice game. Imagine rolling a set of 1,000 dice until you get 1,000 sixes. Puzzle solvers will attempt trial after trial. This is called Bitcoin mining. Once a winning number is found, the miner will verify the transaction details and then propose a new block. Nodes, seeing that a winner has been found, will pause what they are doing to confirm the newly proposed block. If the majority of the nodes agree that the winning number and transaction details are all valid, the block will be added. The successful miner is rewarded with Bitcoin currency, BTC. Proof of work is a resource-intensive process. Bitcoin miners are running high-powered computers 24/7 all around the world. In 2021, Bitcoin miners used as much energy as the entire country of Argentina. Another limitation is that miners are increasingly joining together in mining pools to increase their odds of success. This is perversely incentivizing consolidation rather than the decentralization of the network. Currently, the top 3 pools collectively own more than 50% of the nodes. Proof of stake, an alternative approach, uses a lottery rather than a puzzle to appoint the winning node, who will be given a cryptocurrency reward. To be selected in this lottery, nodes buy stake in the network. Buying more stake is like buying more lottery tickets. It increases your odds of being selected. Since no puzzle solving is required, this is a faster and less resource-intensive method. And for that reason, the Ethereum blockchain is currently transitioning to proof of stake from proof of work, a process widely known as the merge. Bitcoin was built with the goal of creating a digital currency. Issuing and transferring Bitcoin was in fact its purpose. Other blockchains that have emerged since, like Ethereum, were built with different purposes in mind. For example, to encode information about non-financial transactions. Remember, the blockchain is a container that can record any type of digital information. These other blockchains also require nodes to actively participate in the addition of new data, as in the case of proof of work or stake. This participation requires compensation, which most blockchains offer in the form of their own token. This is the cryptocurrency. The Bitcoin blockchain issues the cryptocurrency Bitcoin, or BTC. Ethereum issues Ether, or ETH. And other chains issue their own currencies. This explains in part why we see so many cryptocurrencies. With more and more applications for blockchain, more new chains are constantly emerging, and with them, more cryptocurrencies. Traffic control measures like proof of work and proof of stake slow down, by design, the processing speed of blockchain. The Bitcoin proof of work takes about 10 minutes per block. Since each block carries the information for 2,500 to 3,000 transactions, this translates to roughly about 5 transactions per second, or TPS, on average. As blockchain networks grow, the demand for transaction processing increases. However, the processing speed does not meaningfully improve. This is a significant dilemma, and is the reason why blockchains are often described as having scalability challenges. Centralized technologies are simply more scalable, since they can be upgraded and improved over time to meet increased demand. The Visa network, for comparison, can process around 20,000 credit card transactions per second, 4,000 times as many as Bitcoin. This scalability limitation is often described via the blockchain trilemma. There are trade-offs between security, decentralization, and scalability. A given blockchain can only optimize for two of the three. Highly decentral, secure blockchains, like Bitcoin, will suffer when it comes to scalability. Conversely, highly scalable and secure blockchains are difficult to truly decentralize. For example, if a central authority were to take singular control of a new block validation, the process could move much more quickly. Scalability would go up, but at the cost of reduced decentralization. But a solution has emerged to address the scalability challenges of Bitcoin and similar blockchains: batching transactions together. Blockchain developers have effectively created side blockchains that can process transactions in a separate container. The side blockchain can then periodically update the primary chain. This is like outsourcing or delegating work to the side chains. Imagine that the primary chain is like a CFO attempting to do all of the accounting alone. Using side chains is effectively like hiring a team of accountants who can work and process in parallel, reporting back to the CFO periodically. These sidechains are viewed as building functionally on top of the original chain, and for this reason are called Layer 2 blockchains. To keep up with the volume of BTC transactions, the Bitcoin blockchain relies on Layer 2 chains like one called the Lightning Network. Ethereum has its own Layer 2 chains, designed specifically for the Ethereum chain. These are often described as Rollups. Bitcoin was designed to be a cryptocurrency and is primarily a ledger for recording Bitcoin transactions. Ethereum, conversely, was built with a broad set of purposes in mind and is able to run executable code, like other computer programs. The information that Ethereum can store goes far beyond the buying and selling of ETH. In fact, any number of tasks and applications can be processed on the Ethereum blockchain via the layered structure. Think of Ethereum's main chain, Layer 1, as being like a computer's operating system. Layer 2 is like the software applications, adding specialized functionality. Some of these applications build on top of Layer 2 chains, and these are often described as Layer 3. Layer 2 and 3 chains are themselves blockchains, requiring their own rulebooks and consensus algorithms. Some may also be issuing their own cryptocurrencies. There is a naming distinction to be aware of. Cryptocurrencies issued at these levels are called tokens. The core cryptocurrency asset, like Bitcoin or Ethereum, is called a coin. In any chain ecosystem, there can be many types of tokens, but only one coin. Blockchain layering explains how this unique data storage container can be used to program and process complex information. These layers have created a new universe of blockchain features and functionality, each blockchain with its own unique ecosystem. In the next chapter, we will explore a few key blockchain use cases and some of the products and systems that make this ecosystem possible.